Okay, so we continue with the cement. Typically, ordinary Portland cement will have 65% calcium oxide. So, if I want to find out how much calcium carbonate I require for 1 ton of cement, that will be simply from the reaction, because calcium carbonate breaks down into calcium oxide and carbon dioxide. This has got a molecular weight 40, this is 12 and this is 16 into 3. So, we will make it 52 plus 48, 100. 40 plus 16, this is 16, 56, and this is 12 plus 32, 44, right. This is what it is. So, if I want to produce 1 ton of cement, right, 1 ton of cement, then I go to, I can calculate it, because 0.65, 1 ton of cement will have 0.65 ton of calcium oxide, 0.65 ton of calcium oxide, right, 0.65 ton of calcium oxide. Okay, let us see this, quickly look at this. 100 lime produces 56 unit of calcium oxide, that is what we have seen. Calcium carbonate had the molecular weight of 100, calcium carbonate we said was 100, produces calcium oxide 56, plus CO2 44. So, 56 and 44 units of, thus if I look at this. So, 1 ton of clinker requires how much calcium carbonate? 100 by 56 unit of calcium oxide. So, 56 units of calcium oxide require 100 units of calcium carbonate. 0.65 ton of calcium oxide, you will require 1.16 ton of calcium carbonate, only from the calcium oxide, right. So, raw material you will require 1.16 ton for calcium oxide containing raw material. Okay. Plus I have got rest of the things. So, 1 ton of cement I want to produce, the 0.35 tons will be other materials. There will be some amount of evolution, some amount of material that will also be lost from there, like magnesium carbonate will have also carbon dioxide contribution. Some nitrous oxide, sulfur dioxide, etc. is also produced little amount, moisture also little bit will evaporate out, right. So, but anyway you can see that 1.16 plus 0.35, that is 1.35 is the rest, because 0.65 was calcium oxide in cement, 0.35 will be less. 1 ton of cement will have 0.35 tons of other materials, leaving all the details a little bit away, because they are smaller compounds. So, my total raw material requirement will be this plus 0.35, which would be 1.51, 1.51. So, you will need at 1.5 around 1.51 tons of raw material to produce 1 ton of cement, right, 1 ton of cement. And you will produce how much carbon dioxide? Carbon dioxide that you will produce is, you produce like from 100 you produce 44, from 1.16 how much you will produce? From 1.16, so from 100, let me just write it like this, from 100 you produce 44. So, 44 divided by 100, and you are using now 1.16 tons of calcium carbonate. So, this will give you how much? This will give you some value like 0.51. So, 1.16 into 0.44, into 44, yeah, 44 would give you, we can just quickly calculate it out, right, 1.16, right. So, if you 44% of that, actually 0.44, something like this, somewhere 0.52 or 51 around that will come, tons of carbon dioxide you will produce. You can see that you can produce that much of carbon dioxide. So, approximately 0.51 carbon dioxide. So, all other materials are solid, thus total would be nearly 1.5 ton, that is what I was saying. Maybe 1.16 limestone combination, 0.2 clay, 0.1 to 0.02 to other materials. So, that is how this is. So, you require nearly 50% more raw material, nearly 50% more raw material, and nearly 50% of 51% of it goes as carbon dioxide. What 1 ton of cement means, direct production because of clinkerization is around 0.51 ton of carbon dioxide. So, 1 ton of cement would actually produce 0.51 tons of carbon dioxide just because of clinkerization, chemical reaction. I have not taken something else, not yet, I have not taken something else, right. So, this is what it is diagrammatically. Raw material cement, this gives you 1.47 because I have taken 0.65, some people might take 0.6, and so there could be some variation. So, this diagram taken from cement technologies ideas. Raw material extraction and transportation, first process, crushing is the next process, grinding is the next process, clinker production is the other process, cement production, packaging, distribution, cement 1 ton. And what it produces then? Some amount of dust. So, 1.47 tons approximately of that order, it produces around 2.2719 kg, not in terms of tons anymore, that would be too much. So, that much dust, 800 kg of carbon dioxide, that is 0.8 tons, right, 0.51. So, half, near half, because magnesium carbonate I have not taken into account. There will be some amount of magnesium carbonate also, there will be loss on ignition. So, some free carbon could also be a very small amount. Then carbon monoxide also comes in, NOx comes in, sulfur dioxide, hydrocarbons, particulate matter, volatile organic compound, solid waste, because I have not taken one thing here, the fuel. The fuel will have, fuel, two things. NOx is produced at high temperature, nitrogen is an inert material, but since you are heating up to a very high temperature, nitrogen and oxygen can react and form NOx depending upon the situation, right, nitrous. Sulfur would be there, volatile organic compound will be there in the fuel, raw fuel that you use for production of burning process. So, all this comes solid waste and some liquid waste. So, that is typical, some idea. So, you can see that what you are producing dust, you are producing carbon monoxide and carbon dioxide, NOx, sulfur dioxide, some hydrocarbons, and then particulate matter, volatile organic compound, etc., but then large quantities of course the carbon dioxide. This is 800 out of 0.8 tons out of 1 point. So, nearly 50% you produce there. In fact, it could be more because of fuel it would be coming, depending on fuel it will be coming. So, we will see that. So, fuel generally required is 100 to 200 kg per ton of cement depending upon the process. An efficient process will require less fuel, somewhat less efficient. So, generally 100 to 200 kg of per ton of cement, that is what you need, fuel. And the fuel will burn to carbon dioxide, some portion, some of course we will see that fuel what are those. So, 44, thus carbon dioxide generated is the fuel. If I say percentage of carbon is known in my fuel. So, depending upon type of fuel you are using, type of burning process you are using, and you can't use any you can't just heat them up, you need uniform burning. So, what is done? Fuel is fed together with your raw feed, mixed up together, then you do the clinkerization or preheating process, then you do preheating process. Basically the waste heat from the kiln also, hot gases goes to the preheater. So, there is some recovery, etc., etc. So, you actually basically mixing is required, mixing is required. So, I could not have used electrical furnace, which would have different burning would not be. So, the technologically it is not possible. So, this if you look at it 44 by 12, right. So, 100 kg we said is 0.1 ton, I need 100 kg of fuel means 0.1 ton. So, if I use 0.1 ton then I get 0.37 tons of, and let us say this 100 kg is pure carbon. The fuels those are used are usually pet coke, petroleum coke, right, that you get from the destructive distillation of the crude. From the crude, when you actually petroleum refineries what they do, they actually not destructive distillation, sorry, the fractional distillation they do. So, the one that comes down below, that is the largest solid mass, the others at different temperature different things will come out, right, like your gasoline and petrol etc. They separate out, whatever is left is a pet coke. So, that pet coke has got high carbon content, furnace oil sometime, or some very high good varieties of coal with very low ash content and so on. So, that would be then grinded together. So, if I use 100 kg or 100.1 ton, then I would generate 0.37 carbon dioxide, because 100 kg means all carbon, let us say 12 unit of carbon produces 44 unit of carbon dioxide. So, 0.1 ton will you produce this, or if I am using 200 kg then 0.74, and I already had 0.51 from the clinkerization process. So, you see 0.51 plus 0.37 will make it 0.88, and if I add 0.74 to 0.51 it will give you 1.25, right. That is why on an average, of course, some electrical energy is also used, various kind of, there is like systems here and there, they are also used. So, that is why people say what is the average of this one? Roughly around 1 ton. So, 1 ton of cement, OPC cement produces 1 ton of carbon dioxide on an average. It could be less, 0.75 to even 0.1.25. Some processes they might need even slightly less. So, that is why so some people will people will say 1 ton of cement produces, on an average it is expected that it would be around 1 ton. 1 ton of cement will produce 1 ton of, right. So, if you see that limestone 95% calcium carbonate, shale, right. So, this is 80 parts, this is 20 parts. That is what the raw feed typically quarried land quarried material would be there. So, this will have silica 52%, alumina 14.2, iron 8.7, calcium 1% or so. Typically similar could be the composition. This will have silica 3.3, alumina 0.7, iron 0.2 and calcium 53.5%. So, this could be some typical composition of the shale and the limestone, right. Now, then I mix them into 80 to 20 parts to go to the mill, right, then raw feed etc., and from there it goes to the burn. Now, the point that is here is, you see some of this material like no limestone you will get pure limestone, in nature pure limestone will not be available. And what is abundant in the earth crust? Clay or clay minerals. You see earth crust is full of clay minerals, right. So, impurities are also clay minerals. That is why you will have some silica, some alumina, some iron, minimum at least this. You might have some of the other things coming as impurities in the system. So, these are the small quantities. So, this is what it would be there, although you would have liked to have everything lime, that never happens, and somewhere they select the quarry will having appropriate proportions of lime and clay, otherwise they just mix shale from nearby places. So, 20 parts, 80 parts, if you calculate this out you will find out. So, it will be 53.5 into 0.8, and this will have silica 0.2 into 52.8. You can calculate the proportion of each of the components now. This is what it would be, and that go to the mill, and then the final product that would have 13.2. How? Because 52.8 into 0.2 plus 3.3 into 0.8. How much does it make? How much does it make? 10.5, roughly around 10.5 from this, and this is 2.6, 13.1. Well, I think I have done the calculations more or less okay, and this is important. C is important. C would be 0.8 into 53.5, 0.8 into 53.5 plus 1 into 0.2, so 0.2. So, that's what is coming. So, rest all are simple. So, that is how the raw feed then this is the kiln, and then if you are the coal, of course, coal, if you are using coal for burning, so coal goes in, whose coal goes in, and then this will have some ash left, 51%, etc. So, then you can, from this you can actually calculate out, because this will have silica, alumina, 9 point, and unburnt carbon is 1.6, and these are percentages in this one. 10 to 15% ash is there. So, you can actually find out final product would be, silica was 13, this was 43, and limestone was 43, and some small ash might come from here also put together. This will show you something of this kind, right. So, because percentage wise, if you see even in this one, 43 plus 2, let us say 45 plus 3, 48 plus 13 would make it 50, 60 something, out of which 43 is the limestone. This sum total how much it is? 13.2 plus 3.4 is 16.6 plus this is 1 point 16.6 plus 1.9 plus 43 point, right, 61.5. So, 43 out of 61.5, so 1.16 is to 1 ton, that is what we said, to like 6.65, because final 1.16 that gives me 0.65. So, this will fit into that kind of ratio. So, that is the final product of the clinker will come if you calculate it. So, that is what it is. Okay. Now, some more things, these are the two compounds. So, I will come to this, state this a little bit later, and magnesium carbonate. Now, from the chemistry we know the amount of kilojoules you require per mole, enthalpy changes, or amount of energy you require to which would be required to break this, amount of energy required to break this, because you are giving energy. So, how much energy required from chemistry we know, for calcium carbonate, calcium oxide to carbon dioxide you want to break, this is the delta HR, change in enthalpy, that is the heat content. So, you have to at least supply this, but the efficiency of the system would be there. There is something called free energy. I am not going to the thermodynamics part of it, but let me just quickly explain. This is the change in heat content of the material, internal heat of the material. Now, while changing this internal heat of the material from this level to this level, once you have changed it, you have raised it to higher energy level. So, it can come back to its original level again, but then it will not be able to release all the energy, because of some of the energy will get converted into what is called entropy disorder. So, the free energy is the one. How much is the free energy you have added to the system? Free energy is enthalpy minus whatever is lost through entropy. So, if you want to calcium oxide and carbon dioxide you have produced, supposing I am in an ideal situation, I am again, because they will try to automatically react, try to go to the calcium carbon stage, you have given energy to break this, they will try to come back to their natural state. That is what happens. I mean, obviously, if you add water, calcium hydroxide, carbon dioxide will go to calcium carbonate, as you know. So, supposing I am able to, this will have a tendency to go back to calcium carbonate state. Supposing I am trying to do that, right, I will not get this energy I will not get back. I will get only part of it, because part of it will be lost in entropy changes, disordered changes, which is Q by T. Okay, I do not think I will go into that. Similarly, for magnesium carbonate, this is the amount of kilojoules per mole required. So, typically the components could be something like this, green feed could be something like this. Let us say shale is, shale is 25%. So, silicon oxide to calcium oxide, this carbon dioxide has been taken together here 43, etc., etc. So, something like this, and one can calculate out how much is this change. One can also calculate out this. Now, I am not going to the thermodynamics part of it, but for the process, it is the process where entropy less is, or it is called this, where I take care of the entropy or work potential, I call it exergy. Sometime I mentioned this in the last class. So, there are two kind of efficiencies, energy efficiency and exergetic efficiency. So, for the process, exergetic efficiencies are very important. Energy efficiency is always important for our purpose, but some of them you can't help it, because chemically natural process it is this. But your fuel system, you can always look into how efficient the fuel system, and your process overall how efficient it is. So, 1 kg of clinker one can show how much energy would require, because for this combination of 43 calcium oxide, for 43 calcium oxide 100 minus 35, because 35 is the carbon dioxide going out, divided by production of calcium oxide requires this much kilojoules of energy. So, this much kilojoules I can find out. So, this is 100 minus 35 is the solid part, and it requires like how much this is for for magnesium or calcium. This is totally both for magnesium and calcium, both are taken into account. Yeah. So, this is calcium oxide. For calcium oxide, this is the delta H for calcium oxide, molecular weight of calcium oxide, and this is the how much was this 158. Yeah, this was 158, this is 99.7. So, this is for magnesium, this part is for magnesium, and this part is for calcium. So, 43.1% was calcium oxide. In the cement you will have percentage wise 64.89, something like that is being conceived, summing up, leaving up the carbon dioxide part of it. So, sum total will give something like this, that is the part of the cement, solid 100 minus 35. So, one can actually calculate out how much energy kilojoules per kg of clinker required. This will work out to be 2.217, because 158 is required for 158 is the enthalpy changes required for calcium oxide per mole, right. So, if you have I mean for 1 ton of cement how much calcium oxide is there, and how that divided by the molecular weight. So, the molecular weight comes into picture there. 40 is the calcium oxide, is more precisely taken 40.08 and 15.99 instead of 16. So, this is the molecular weight. So, for 1 mole this is the heat required, right, 1 mole this is the heat required. So, 158 kilojoules will be produced from this many kgs. From 43.1 kg how much will be produced, because 43.1 was the sum total. Here if you sum it up, for this is the 43.31 calcium oxide. So, this is this, and the proportion of calcium oxide in the system is 64.89, because exact calculation has been done. So, this is the amount of heat that enthalpy changes required for calcium carbonate to calcium oxide. This is for the magnesium part of it. How much was it? Magnesium percentage is, magnesium is 99.7 is the heat enthalpy changes, and magnesium is 99.7, total 64.89 is the solid mass actually, and this is the magnesium oxide molecular weight. So, this way if you calculate out, you get 2.217 into 10 to the power 3 kilojoules per kg of clinker. So, you can calculate this out. calculate this out. This is the energy required or enthalpy change required, not energy, enthalpy change required to produce 1 kg of clinker, 1 kg of clinker. So, this is per kg of clinker. One can do also exergetic calculation. I am not really interested in this right now. So, this one can calculate out. Supposing I use fly ash, supposing I use fly ash some 25%, then fly ash would have different combination. Obviously, I am saving on to the enthalpy or energy part of it also, because the fly ash is straight away available. I am just adding it or grinding it at best. So, therefore, you can see that 75% clinker, 35% fly ash, 75.75 multiplied by this much and enthalpy changes would be there. The other one would not have anything. We are obviously ignoring the grinding part of it. So, when you use such material such as fly ash, obviously your energy required will be reduced. I do not think I will. So, you can see that it is point, how much was the percentage? I said 65 and 30, 75, 35 it will not be. So, I multiply everything by 0.65. So, 2.217 multiplied by 0.6, 2.217 into 0.65, that is what it will give. So, using those materials which are already waste material, which I can add directly, obviously would save into my energy. Besides, wastes are also absorbed. So, eco footprint scenario, this would be much more advantageous. Okay, I do not think I will look into this. Typical fuel for cement, petcoke could have 97% carbon. The heavy fuel like furnace oil and similar sort of thing, 86, 12%. So, this is very much preferred actually. This is very much preferred. In fact, in India most of it they use, but there is something more than that. I will just come to this. There is something more. Most of the cement plant, I mean at least two major plants that I have looked into in India, which have like Ambuja cement for example in Gujarat, Ambuja Nagar, or Wadi of SEC, which I happen to have visited. Similar ones must be there elsewhere also. They actually use all sorts of alternative fuels, which I will come and discuss later on. So, for example, near Ambuja cement there are a lot of plastic and paint factories. So, all those can be used as alternate fuel as long as they do not produce any toxic, do not release any toxic gases to the atmosphere, toxic gases to the atmosphere. So, they practically use all, the not only that, the double advantage they get is the people who are supposed to dispose those waste, now they do not have to dispose, they might give them free of cost, right. All that they have to do is analyze them for their chemical and mineralogical composition and all that, and see as per standard how much is the toxic emissions out of those, kind of toxic gases emission out of those after burning. So, based on that they do. This is obviously would be relatively, this comes from the petroleum, I mean refineries. Now, so generally they will have carbon, hydrogen, oxygen, nitrogen, sulfur. So, when you heat them up, obviously this goes to carbon dioxide, this is water, no problem, and the oxygen, some part is there very small, but at high temperature they produce that NOx, not this oxygen, atmospheric oxygen as well, and sulfur dioxide. So, that is how they come. And in this one obviously this is there may be other compositions of fuel of varieties of kind, but alternate fuel when we talk about we will see that what is the advantage. So, there is something called heating value, megajoules per kg, that is important, how much heat you are getting. We have seen the energy required, which is around 2.217 into 10 to the power 3 was it kilojoules or megajoules, kilojoules per kg, kilojoules per kg, right. So, it would be kilojoules, and this so how much you would need, how much fuel you need, that would that you can find out from this, plus the efficiency factors will be there, several efficiency factors will be there. So, consumption per kg of clinker is therefore, since this will be less because this has got more carbon, right, and typically the consumption is 0.096 kg per kg of clinker. Now, multiply this by this, how much megajoules you are getting? 33.2 into 0.096, right. How much it would be? Even if I take it to be 0.1, it will be 3.3, roughly around 3.32 megajoules or 3.3, around 3 megajoules I will have, which means that 3300 kilojoules, right, 300, this is 3300 kilojoules per kg, which would mean actually per ton how much it will be. I should multiply this by 1000, which will mean 3.3 megajoules per ton. Am I right? See, 0.096 multiplied by 33.2, because the megajoules per kg is the heating value. So, it will generate that much heat. So, multiply by this, roughly I have multiplied by 0.1, 0.096 is 0.1. So, it will give me 3.32 megajoules per kg of clinker, right, per kg of clinker, okay. I mean this is heating value is, heating value per kg of this pet coke. So, I need 0.096. So, this will give me, multiply by these two, I will get 3.32 megajoules, because this is this much I have used for 1 kg of, I require for 1 kg of clinker, I will need I will generate 3.32 megajoules from this, it is coming that 3.32 megajoules for 1 kg of clinker, that would be generated, that would be, if I want to generate 1 kg of clinker, I will need from the pet coke, this is what I will get the energy. And this is for 1 ton, I just multiply this. So, 3.3 into 10 to the power 3, and how much was the requirement from enthalpy? 2.217. That is why I was trying to calculate it out, because if I will do this 2.217 kilojoules actually. So, you can see the orders changes, there are a lot of here and there will be a lot of losses and efficiency you can see. So, anyway, so this is a typical composition of somewhere. We defined two terms called heating values. Amount of heat released when a compound undergoes complete combustion is heat of combustion in kilojoules per mole, that is what we know. Heating value or calorific value of fuel is amount of the heat released during the combustion of a specified amount of heat, say kilojoules per kg, right. So, this is calorific value in other words. Now, there are two heating values, higher heating value and lower heating value, right, lower heating value. So, all the products of combustion attains original pre-combustion temperature. That means, you have a like pet coke, you burn it, the heat is generated, even the flue gases at the top, if it comes to the ambient temperature, then this heat is all utilized, that is upper limit. But actually this will not be the case. Assumes water vapor as vapor, so latent heat goes, water remains as vapor, and some gases which is at high temperature, that heat, so the lower heating value assumes a water vapor, particularly water vapor, because some less amount of heat actually you can realize, because latent heat of vaporization will not be available for your work. Obviously, there are other efficiency losses, like hot gases going out, some energy is gone there. So, this is important for raw material, because higher the heating values, it will require less fuel and obviously lesser carbon dioxide production. So, the alternative fuels that are there, people are using waste tires, biomass, used solvents, sewage slush, municipal solid waste, all other waste, and so that is what we talked about. Now, advantages, this is what we looked into, and this is what we have looked into. Now, we will come back to this in the next class, but just I want to finish here. Advantage of using this is, whenever you take this into account, whenever you use this sort of material, they do not go into accounting. So, the eco footprint of the factory will come down. Supposing I am using waste material, this does not go into accounting, and the factory gets the advantage, that is eco footprint comes down. So, all the environmental control organization, they really encourage this, right. So, we will just come into this. So, damage index from various gases is something like this, I think I mentioned, right. Okay. So, this we will look into. So, relative emission from cement comes out to be 800, I have shown you earlier. Methane was hydrocarbons, and nitrous gases were 1.57. So, I think this gives you. So, we will look into that in the next class.